Okay. So the last time we finished with an interesting claim that any locally free sheaf and in fact this is the same as torsion free sheaf. On a curve C has a filtration such that the successive quotients are all line bundles. There's the same as invertible sheaves. So we proved this, and this is some really deep geometric statement, and some people study those filtrations for many years. Okay, so let's go on. So today we will define. Well, last time we defined the degree of a divisor. D on a curve C. And today we will define degree of an invertible sheaf d of L. Well, again on this curve C, but it will require some preparatory work. So let's start with this work. Well, I mean, we know that any invertible sheaf is of the sort L is necessarily OC of D for some divisor, and then the degree of L will be just the degree of this divisor D. But we must check that this is well defined. Yeah, that if there are various ways to identify an invertible sheaf with this OC of D, and for all the choices of divisor D, they will have the same degree. So we need to check this. Okay, let's start going in this direction, and so let's take any sheaf F, torsion-free sheaf. On C. Let's take any effective divisor.
Почему принципиально, что он без кручений? Это как-то влияет на общую конструкцию?
You mean F or whom?
F.
Well, I didn't say anything yet, so the question does not make sense yet. Well, let me say something first. Okay, we take an effective divisor like, for example, 1 point plus twice another point, something like this, and then we can consider F tensor OC of D, and this has a rather concrete incarnation. So recall that we have this big sheaf of rational sections like this, which contains the original sheaf F, and the sheaf of rational sections is localization of the space of rational sections, and this is a finite dimensional model over rational functions, over the field of finite dimensional vector space over the field of rational functions on our curve. And then if we take the corresponding localization, then this contains various fractional ideals, in particular OC of D, a fractional ideal. And so we can multiply. And the claim is that F tensor OC of D is nothing but the multiplication F times OC of D. So I once again in this second interpretation, I use that F lies inside this big constant quasi-coherent sheaf that is acted upon by rational functions, and OC of D also lies inside the rational functions, and all those both things are called F of D for short. Fine, and now for an effective divisor, we have a notation. F restricted to D is the quotient F modulo F of negative D. Okay, so this makes sense for an effective divisor. Okay, so for example, if D is just one point in our curve, then the restriction to this divisor is just the fiber, which is sometimes denoted the same way as the stock, or sometimes denoted F restricted to this small point C. Okay, but now say if D is twice this point, then in a sense, well, theoretically, this is just one point, small c, with multiplicity 2. Okay, so nothing changes set theoretically from the previous example, but F restricted to this divisor will have well, what to say it, maybe the dimension over k, I should say, of this restriction will be twice the rank of F. Okay, so it's not just set theoretic. And well, maybe let me formulate it as a general claim that is obvious, but still let's have it for future reference. That first of all, this restriction to the divisor is a torsion sheaf supported on D. This is absolutely obvious as everything in this lemma. Now, last time we defined the divisor associated with the torsion sheaf. Right, it was the sum over the support of this torsion sheaf of the points with multiplicities. The multiplicities were equal to the dimension of local sections around these points. So this divisor over this torsion sheaf is just the rank of F. It's a number, multiple of the original divisor D. Okay, and finally, the dimension of global sections over our base field of this torsion sheaf is the product of rank of F times the degree of divisor D. Okay, this is all absolutely clear, but we just need to document it. Okay, and now let's study.
Я можно спросить?
Yes, certainly.
Вот по пункту Б вот не очень понятно, даже если мы локализуем пучок, как будет возникать ранг F. Там же нужно, ну вот если по определению расписать Димонов D, мы должны найти дивизор, фактор.
It's called in Russian. It's called divisor.
Дивизор, да.
Yes.
Дивизор вот этого фактора F по F минус D, это будет какая-то сумма по всем точкам, размерностям, локализациям вот этого F фактора F минус D умножить на точку. И как эта сумма соберется в ранг?
Well, for example, you may use this result at the top of previous page. Yeah, so you can filter your torsion-free sheaf F such that the associated gradient is the direct sum of invertible sheaves, and invertible sheaf locally looks like just the sheaf of functions, the structure sheaf. Yeah, and then everything is additive here, and for a structure sheaf this is also obvious, so you may do it like this, for example.
Спасибо.
Welcome. Okay, so now let's go to some applications. So we'll need to study the morphisms between curves and the push forwards and pullbacks of torsion-free sheaves. Something like this. So now we'll need two curves, and they will be both smooth, projective, and we already proved that it's the same as proper curves. And we also proved that they are uniquely reconstructed from their fields of rational function. Such fields, and we have a morphism from C to S, and then we know that it's equivalent to the embedding from an embedding from K of S into K of C.
Почему это морфизм, он суръективный будет в S?
Right, absolutely, yes. So we require this surjective.
Определение так строится.
Yes, so certainly there are morphisms that go just to point, but these are not very interesting, and we will consider more interesting surjective morphisms, and we'll prove the following claim that I already formulated a week ago, that first of all, F is a finite morphism. Second, that if F is a torsion-free or locally free sheaf, on C, then its direct image is also torsion-free or locally free on the base curve S of rank that is the product of rank F times the degree of our morphism F, and well, in particular, the direct image of the structure sheaf OC is a locally free sheaf on the base of rank equal to the degree of F. So let's prove it. And first of all, let me recall that the degree of F, by definition, is the degree of the field extension. So K of C over K of S. Okay. So then, first of all, by construction, the curve C is the normalization of the base curve S in its field of fractions in K of C. Okay, and hence F is finite. Okay, now let's go prove B. So the direct image of F is torsion-free. Just you see, somehow for direct image, you essentially do nothing. I mean, to define, to study the direct image of a sheaf, you just you restrict the scalars to the structure sheaf below of the base, from C to S. Okay, so if it had no torsion upstairs on C, it will still have no torsion after restriction to the structure sheaf of S. So here nothing happens, and if you take the rational sections of F, then it's the same as rational sections of its push forward. In this sense, nothing happened. And also, I claim that this direct image is, well, first of all, it is quasi-coherent. We proved this some long time ago in December. We only need to check that it is coherent, and then it will be automatically locally free. Yeah, because it's torsion-free and coherent, so locally free. So let's check that the direct image is coherent. That is finitely generated OS module. But this is also clear since OC is a finitely generated OS module, or you may phrase it equivalently that the direct image of OC is a finitely generated OS module, since F is a finite morphism. It's just a tautology, but our sheaf F was a finitely generated OC module. So combining those two, we see that the direct image is a finitely generated OS module. Yeah, just because it's a finitely generated module over a finitely generated module over OS. Okay, and finally we have to compute the rank. So rank of the push forward of F is the dimension over the field of rational functions on the base of rational sections of the push forward, but the rational sections of the push forward are the same as rational sections of F, and so we get, sorry, for this this dimension of the rational over the rational functions on C of the rational sections of F times the dimension of the field extension over.
Да, как вот этот последний переход был сделан?
Which one? We didn't.
Последнее равенство.
Well, if you have, well, let me write the last thing and then answer your question. Rank F times degree of F. And now answering your question, if you have V, a vector space over the big field K of C, then the dimension of V over the small field is the dimension of V over the big field times the degree of the extension.
Спасибо.
Welcome. Okay. So there we are. We proved this lemma. So once again, this lemma was about push forwards of locally free sheaves under surjective morphisms of projective curves. Yeah, it says that the direct image of locally free sheaf is also a locally free sheaf, and you can control the ranks of these push forwards. And now we have this very important notion of the pullback of dividers on curves. And well, let me first give a definition, and then I will comment on this. So E will be a divisor on the base curve S, and we want to define its pullback, denoted like this, a divisor on C, And so let me give the definition. We consider the corresponding line bundle, invertible sheaf, OS of E, and then we take the pullback of this locally free sheaf on C, and any locally free sheaf, any invertible sheaf on C is associated to a divisor, and so this is C of some divisor, and this divisor is our pullback by definition. It is the definition. So, well, when the pullback here is considered as a fractional ideal on C. Okay, so this way we define the homomorphism from the divisor group on S to divisor group on C. Okay, and now let me make a comment that suppose we have well, at least locally, a morphism like this, some twofold cover. But it's ramified over some point S in the base. Yeah. So this is S, this is C, and for a typical point here, its pre-image consists of just 2 points. Maybe let me call it, well, let me call it S. So F inverse of S is C1 plus C2. Here C1, and here C2. Okay, and then this is also, well, maybe I should say that this is the union like this. And yeah, that the pre-image consists of 2 points. But then from the point of view of divisors, if I take an effective divisor consisting of just 1 point, then I get the divisor upstairs, the sum of the points in the pre-image. This is very natural, but if I take a point here, where we have a ramification, then its pre-image will be just 1 point C0. So the pre-image of this special point downstairs will be just 1 point upstairs, but still you say that at the level of divisors you still have the same degree, so they twice times divisor C0. Okay, so this was set theoretically, and this was divisor theoretically. Okay, so it's more or less the sum of all points in the pre-image, but with multiplicities, and the multiplicities are assigned according to ramification. So I will explain the exact meaning of these words later on, but so far just approximately, I hope it's approximately clear. Okay, and now the key lemma for preparation to degrees calculation is as follows: that the degree of this pullback divisor is the degree of the divisor E itself times the degree of our map F. So in the above example, the degree of F was 2, and clearly we had this formula. So now let's prove it in general. And now the left hand, both sides are additive in the divisors on the base. So it suffices to take E just 1 point with multiplicity 1, like small point S. Okay, and then let's compute. We have the degree of the pullback of this simplest possible divisor. We compute it just by definition. So this is by definition the dimension of the or just global sections. I don't know. There's a skyscraper sheaf. So let me just write dimension over K of the base field. Modulo OC of negative pre-image of S. This is the so we're interested in this divisor pullback of S. Yeah, so we don't yet know what it is and how to compute its degree, but just by definition of the degree of divisor, this dimension. Okay, and now we can rewrite this as the dimension of pullback of the structure sheaf OS over the pullback of structure sheaf OS twisted by this point. Okay, and then we get the dimension of the global sections over.
Извините, пожалуйста, а как был предпоследний переход сделан? Это просто по свойствам.
You mean because the structure sheaf of C is the pullback of structure sheaf of S, just by definition.
Все, спасибо.
And the same for subsheaves. And now, since the pullback is right exact, it takes quotients to quotients. The quotient of OS modulo OS minus point is just the structure sheaf of this point. Okay, and so I have this equality. Now this is the dimension of the push forward. So we go back to the base curve. Like this. Okay, and now here we use the projection formula. The projection formula says that if you if you take any sheaf downstairs on S, on the curve S, and you pull it back to C and then push forward back to S, then you don't need to compute this for all the sheaves. You just need to compute it for one structure sheaf, and then you just tensor with this. So let me write this down. Next page. For any coherent say G on the base S, if you wanna pull it back to C and then push forward back to S, then you do this once and for all for the structure sheaf OS, and then tensor with G. Okay, they are very useful projection formula, and it's a local computation, and locally it's an obvious property of expansion and restriction of scalar. So you take the local ring on S, local ring upstairs on C, and just extend and restrict scalars. Okay, so this is so, and now let's apply it to our situation. In our situation, the sheaf G was just the skyscraper structure sheaf of this small point S. Okay, and what we get is the dimension of global sections of this point S, small point S, the push forward of the structure sheaf of the curve C, restricted to this small point S. Okay, but then we know that this is the rank of push forward of the structure sheaf of curve C, and we know that this is the degree of F, and well, if you want, this is degree of F times the degree of our divisor S, or 1 point divisor, and we're done. Okay, so in a sense, once again, the result of this lemma, the statement of this lemma is pretty intuitionally clear, but the rigorous proof is not too short. Okay, but now given this result, we can finally define the degree of line bundles. So we're almost there, and now let's consider a rational function f. So it will be morphism from C to S that is just the projective line. So in other words, f can be viewed as a rational function. On curve C, and then we define the divisor of this function. Well, so on the one hand, you take f times the structure sheaf. There's a fractional ideal, and necessarily this fractional ideal is of the form OC of negative of some divisor, and this divisor is negative divisor of f. So this was a definition. On the other hand, you can view this function as a morphism to projective line, and well, let's say equivalently, you have on the projective line, you have 2 points, 0 and infinity. So their pullback will be the 0 divisor of f and the infinity divisor, the pole divisor of f, so to say. So the divisor of f is the pullback of the difference 0 minus infinity. So 0 minus infinity is a degree 0 divisor on P1.
Именно вот эти две точки были взяты в качестве...
Well, just so the divisor of f is the divisor of zeros minus the divisor of poles, by definition. So that's what you get. Okay, or maybe if you want, we can phrase it differently. So in other words, let t be the coordinate on the projective line. Then, according to the first definition, the divisor of t is really 0 minus infinity. Okay, and now the pullback of the divisor of this coordinate function is the divisor of f. Okay. Okay. So from the description, it follows that the divisor of any function has always degree 0. And this is the corollary of the previous lemma, because the degree of divisor 0 minus infinity on P1 clearly is 0, and the degree of divisor of f is, but by the previous lemma, the product of degree of the divisor downstairs on P1 times the degree of f. It's 0 as well. Fine. So the divisor of any rational function and this is called a principal divisor. Oops, sorry. Has degree 0. Okay, and then we, as a corollary, well, okay, let me formulate it this way first. Let's define the Picard group pic of C. By definition, this is the group of all divisors modulo the subgroup of principal divisors. Because clearly principal divisors form a subgroup, right? If you have divisor of one function plus divisor of another function function, then this is clearly the divisor of their product. Okay. So what was the corollary? The corollary was that this Picard group is the union over all degrees of the corresponding subsets, and say the pick 0 of C is a subgroup. Okay, so I mean the degree of divisor is well-defined modular addition of principal divisors. Okay, when you add a principal divisor, the degree does not change. So this partition of all divisors according to their degrees descends to the quotient group Picard of C, and this is what is used in the next home assignment, in today's home assignment. Fine, and then also maybe another corollary. Is that we can define degrees of invertible sheaves or line bundles. So given an invertible sheaf L, we define the degree of L as the degree of any divisor D such that L is isomorphic to O of D. Okay. So when we know that any invertible sheaf, just when we started studying invertible sheaves in December, we realized, well, in case all the local rings are UFD, but this is the case for smooth curves. So we realized all the invertible sheaves as sheaves of fractional, as invertible sheaves of fractional ideals, and any invertible sheaf of fractional ideals is of this sort. It's associated to a divisor, right? But it depends on the embedding of this locally free sheaf into the field of fractions. So there are many ways to realize a given invertible sheaf as OC of D, but the degree is well defined. That's the point of this corollary. So this degree of L is independent of the choice of D. Indeed, if D1 and D2 are such divisors, so OC of D1 is isomorphic to OC of D2 and is isomorphic to L, then D1 and D2 are the divisors of rational sections. S1, oh, sorry, maybe, okay, S1, or maybe, let me say, sigma 1, sigma 2 of our invertible sheaf L, and hence sigma 2 is some function, some rational function f times sigma 1. F. Okay, and this means that the divisor of sigma 2 equals the divisor of sigma 1 plus the divisor of F, but we know that the degree of divisor of F is 0, and so the degrees of divisor sigma 1 and sigma 2 coincide. Okay, sorry, I need sigma 1 and sigma 2 here. Sorry. That's it. So the notion of degree of invertible sheaf is well defined, and so the Picard group of C equivalently can be defined as the group of isomorphism classes of invertible sheaves on C under the operation of multiplication, tensor multiplication, and again we have the union over all degrees like this. So these are isomorphism classes of invertible sheaves of degree D. Okay. So once again, to relate the invertible sheaves to divisors, you need to embed, to choose a particular representative of your invertible sheaf and embed it into rational functions as an invertible fractional ideal. Okay, so there are many divisors giving rise to the same isomorphism class of invertible sheaves. Okay, all those divisors are the same up to adding principal divisors. Okay, and now let me state. Oops. Okay, let me state next lemma. So it's about global section of line bundle and or invertible sheaves, and in fact we'll study this for a long time with some deviations, but essentially till spring and through the spring. So what happens with global sections of invertible sheaves? First of all, if we have a degree 0 sheaf, then it has no global sections. Unless this invertible sheaf is trivial, and then the global sections of the structure sheaf is certainly the base field. We already know this. Now, the second claim is if degree of L is negative, then there are no sections whatsoever. And if degree is positive, then there are not too many global sections. That is, dimension of global sections is at most degree of L plus 1. Okay, so let's prove this. And we start noticing that if there are some global sections, we can choose one. Sorry, if there are some global sections, sigma non-zero section, and then L is isomorphic to OC of D for some effective divisor. Effective divisor D, namely
все его
divisor
коэффициенты
of
должны
this
быть?
section. Why is it effective, you ask?
Да,
Yeah,
почему?
that's the question. It is so because this is the divisor of a global section. It's a regular global section, so it has no poles. It's regular, you see. So it cannot have poles. It can have zeros, not necessarily. Say in the first part of our lemma, the degree of L is degree of D, and if degree of L is 0, then degree of D is 0. But since it's an effective divisor, we see that just D is 0 itself, since it's effective. Now, this proves A. B is also obvious. Since, well, on the one hand, degree must be positive. On the other hand, it's negative, so there's nothing to prove. And finally, let's prove C, and let's prove this by induction. In degree of the invertible sheaf, that is assumed to be non-negative. Yeah, if it's negative, then there's nothing to prove. Or maybe, I don't know how to say it. I mean, what is the meaning of negative dimension? It's an interesting question, but maybe let's skip it. Okay, so if we already know that if degree L is 0, then the dimension of global section of L is at most 1. Yeah, namely, it's usually 0. But if L happens to be trivial, then the dimension is 1. And so the statement C holds true because it's 0 plus 1. Okay, and now let's proceed by induction. So if degree of the divisor is say strictly positive, then you can and D is an effective divisor. Then you can write it in the form some particular point plus another divisor whose degree is degree of d minus 1. Okay, so then we have an exact sequence. Goes to here. It goes to this sheaf of functions with poles on d restricted to this point, and this is 0. So for global sections, we get global sections of the left term goes to global sections of the middle term, goes to the global sections of this restriction to the point, but you restrict a line bundle, invertible sheaf, to a point, so this is just k. Okay, and then you don't know that it's surjection because global sections are only left exact. But anyway, it implies that the dimension of global sections of OCOT is at most dimension of global section of the smaller divisor plus 1, and we're done by induction. Okay, and then maybe let's have a short discussion, because you will need this for, well, it's a very useful fact anyway, and you will need it crucially in your home assignment. So maybe let's call it lemma exercise. That suppose you have a rational function on a curve C with just one pole. Exactly one pole of order exactly 1. And then I claim that this F is just an isomorphism from C to a projective line. And well, under this isomorphism, the point infinity goes to this pole. One pole maybe at point C. Okay, so maybe let's discuss it for a moment. So why is it so? Mark, can you explain it?
Not really, not now.
Okay, and Altan?
I think we have here a ramified covering, as you explained.
Yes.
And so we have so the degree of the inverse image of each point should be equal. So we have the degree of this map equal to 1, and so it should be isomorphism somehow.
Okay. Okay. Yeah. Thank you very much. Let me repeat what Altan says. So the degree of F inverse of 0 minus infinity is 0, and it means that the degree of F inverse of 0 is 1. Okay, so it means that the preimage, the full preimage of 0 is just 1 point. say C0. Okay, and now let's consider for any number say A in our field, let's consider FA, that is F minus A. Okay, then still it has the same pole of order 1. And hence it has a unique 0 of order 1. Hence, F assumes any value A exactly once. And hence, F is an injection. On the other hand, we know that it's a surjection, so it must be an isomorphism from C to P1. Okay, very good. And now let's at least start to study some special effects of finite characteristics. Well, maybe let's call it ramification of morphisms between curves. Okay, so as we discussed earlier today, given a point, so we have a morphism from a curve C to another curve S. They're both smooth projective. And in here we have a point S small, and we consider the pullback divisor. So it's not just theoretic, it's in the sense of divisors, yes? So there's the sum over all points in the fiber, the corresponding points with certain multiplicities. So it's a divisor. And in fact, an effective divisor supported at the set theoretic preimage.
Почему это конечное число точек, а не непрерывное?
Well, because our morphism is finite. Okay, and the EC, the coefficients, are called ramification indices at C. Yes, so for example, when we had this double cover ramified at this point, so it was C naught going to S naught here, then the ramification index at E C naught was equal to 2. But everywhere else there was no ramification, and the ramification indices were equal to 1. Okay, so this is just terminology, and we are going to somehow describe what happens both. Well, topologically, it's maybe somewhat clear what happens, but we want to define what happens, describe it in differential geometric terms and also in algebraic terms. so we'll study it via field extension. So we have the field extension from rational functions on S embedding into rational functions on C. And we will distinguish between separable and inseparable extensions. So in characteristic 0, there is nothing to talk about, but in characteristic P, in finite characteristic, they will behave very, very differently. So we call F separable if F star is, and then also there is an inseparable case. Okay, so this only happens if the characteristic of our base field is finite, some prime number P. So by the basic Galois theory, any F can be decomposed okay, into a purely separable and purely inseparable morphisms.
А когда мы пишем такое разложение, мы звездочки подразумеваем.
Yes, but you see, we have this equivalence of categories, or maybe an anti-equivalence of categories from fields with finite extensions and smooth projective curves, right? So it's the same. Okay, so let's start studying separable extensions today, and next time we'll finish this and also study inseparable. The typical example of inseparable morphism is Frobenius morphism. Yeah, you heard about it, say for lines, but I mean, if our curve is projective line or a fine line, or whatever, but it makes the same sense for arbitrary curve. And essentially, for curves, all inseparable morphisms are just like this, like Frobenius morphism. We will discuss it in detail next time. But today, let's discuss separable. F is separable. And then it is equivalent to the statement that the trace bilinear form from the field extension Kc times Kc to K of S is non-degenerate. Well, X, Y. Okay, and then you have an embedding, say OC into this big constant quasi-coherent sheaf like this, but it's constant. So you have the trace pairing form on it, and you can restrict to the regular functions OC, and the trace from K of C to K of S rational functions induces, well, maybe I should say restricts to the trace say, well, map, or maybe I should say from the push forward of OC to OF linear over OS. Okay, and if you we can take the fiber of this, right? So for any point in the base, the fiber trace at this point, or maybe I should say preceded to this point, is the trace form for the K algebra, the push forward of OC, the fiber at the small point S. Okay, so in other words, trace is compatible with restrictions from OS to all the points in the base. Okay, and well, maybe I'll need a couple more minutes, but let me try. The trace bilinear pairing on the level of field of rational functions again restricts to the bilinear form say B from the push forward of the structure sheaf on C to the structure sheaf on S. Okay, and you see this this pairing for fields was non-degenerate, right? Because our extension was separable. On the other hand, this pairing for fields is obtained from this pairing on the level of rings just by localization. So you restrict to smaller and smaller open subsets, right? So it means that necessarily there is some open subset where this pairing is non-degenerate. An open U in S such that this bilinear pairing restricted to this open subset is non-degenerate. Maybe if you have heard some basic notions of arithmetic, like discriminant of field extensions, yeah. So you choose some basis, and then you write down the trace bilinear form in terms of this basis. So you obtain some matrix, some symmetric non-degenerate matrix, and its determinant is called discriminant, and there's a number, non-zero number, the determinant of non-degenerate matrix, and now this number does have some divisors in the numerator and denominator. Okay, and if you throw away these prime numbers, you obtain this open set where your bilinear form is not degenerate. Okay, so you obtain an isomorphism from the push forward of the structure sheaf. Restricted to U2, it's dual. Okay, and then I'm almost done. Just one more minute. So for a point S in this open set, the restriction B to this small point S is non-degenerate. So it means that the ring push forward restricted to this point S has no nilpotence. Yeah, otherwise the radical in the sense of algebra will be contained in the radical of this form in sense of bilinear forms, right? Okay. On the other hand, we know that the direct image restricted to S is just the restriction of the structure sheaf to this divisor in the sense of divisors, and so this direct sum over all points in the set theoretic preimage of OC restricted to the corresponding multiples. Okay, and if the multiplicity is bigger than 1, like locally we'll have OC times C. Oh, sorry, this is big C, this is small c. Will be locally like the ring of polynomials and local parameter over x to the power EC. Okay, so it will have nilpotence if EC is bigger than 1. So the conclusion is for any point C in the preimage of this open set, the ramifications are all trivial, just one. Okay, so that F is unramified over U. Okay, that's what I wanted to say today, and we'll continue next time. Again, sorry for taking extra 5 minutes. And if you have any questions, then you are welcome.
Можно спросить по странице 7?
Certainly.
Страница 7.
Page 7. Great. Yes.
Можете еще раз повторить рассуждение, доказывающее пункт Б?
Yeah. So suppose it's by reduction to absurd. So suppose there are sections. Yeah. No, I mean there are non-zero sections. Then the invertible sheaf L is necessarily of the form OC of D, where D is the divisor of some of your section, of a regular global section. Okay, but this divisor it's an effective divisor, so it has non-negative degree. But we know that the degree of the invertible sheaf is negative, so it's a contradiction.
Спасибо.
Welcome. Any other questions? If not, let me save the notes and stop the recording.
Получается, сепарабельность нужна была для отсутствия нелепатентных элементов. Так?
Yes, absolutely. Otherwise, you may say that inseparable morphism is everywhere ramified, so to say.
Спасибо.
So it will be bijective on the level of points, but everywhere ramified. Something very strange. It's counterintuitive because we are raised over fields of characteristic zero, like rational numbers or real numbers. Okay, so then let me stop the recording and say goodbye to everybody.